Welcome to this comprehensive guide on implementing the A** pathfinding algorithm using C# within the Unity 3D engine. This tutorial will walk you through each step, from understanding the core concepts to a full implementation and demonstration in a Unity project. A** is a widely used and highly efficient algorithm for finding the shortest path between 2 points in a graph or grid. Its effectiveness makes it an essential tool for game development, navigation systems, and various other applications requiring optimal route planning. Before diving into the actual code, let's establish a solid understanding of the fundamental concepts that drive the A** algorithm. These include nodes, which represent points in our search space, and three crucial cost metrics: g-cost, h-cost, and f-cost. Each node in our grid represents a distinct position or location. The g-cost, specifically, quantifies the actual cost incurred to travel from the designated starting node to the current node being evaluated. This cost typically accumulates as the path extends. The h-cost, also known as the heuristic cost, provides an estimated cost from the current node to the target node. This estimation is a crucial part of A**'s efficiency, often calculated using distance metrics like Manhattan distance for grid-based movement or Euclidean distance for more continuous spaces. Finally, the f-cost is the sum of the g-cost and the h-cost. This combined value represents the total estimated cost of the path if it were to pass through the current node. The f-cost is the primary metric A** uses to prioritize which nodes to explore next. The A** algorithm operates by continuously evaluating potential paths, always prioritizing the nodes with the lowest f-cost. This intelligent prioritization ensures that A** efficiently finds the most optimal path, avoiding unnecessary exploration of less promising routes. Now, let's begin by setting up our Unity project. Open Unity 3D and create a new 3D project. For our demonstration, we'll need a simple scene environment, which will include a basic ground plane and a few obstacles to simulate a navigable space. Next, we'll create the C# script that will house our A** algorithm logic. In the project window, right-click, navigate to create C# script, and then name it Pathfinding. This script will be the core of our pathfinding system. Double-click the newly created Pathfinding script to open it in Visual Studio. This integrated development environment is where we will write, debug, and refine all the core logic for our sophisticated pathfinding system. Our first step in Visual Studio is to define a node class. This class is fundamental, as each instance will represent a single point on our grid, storing essential information such as its position, g-cost, h-cost, and a crucial reference to its parent node. The parent node reference within each node is absolutely crucial for the algorithm. It allows us to reconstruct the final, optimal path by backtracking from the target node once it has been successfully reached by the algorithm. Inside our main pathfinding script, we will proceed to define the grid structure itself. This grid will serve as the digital representation of our Unity scene, clearly delineating both walkable areas and unwalkable obstacles within the game environment. To ensure seamless interaction between our algorithm and the Unity environment, we'll also need to implement utility methods. These methods will handle the conversion between Unity's world positions and our grid's internal coordinates, and vice versa. The core mechanism of the A** algorithm relies on two distinct lists: an open list, which holds nodes that are yet to be evaluated, and a closed list, which contains nodes that have already been thoroughly processed and evaluated. The primary pathfinding logic will be encapsulated within a dedicated method, which we can name FindPath. This method will serve as the entry point for our algorithm, taking both a starting position and a target position as its input parameters. Within the FindPath method, we will first initialize our open and closed lists. We then add the starting node to the open list, marking the beginning of our search, and initiate the main while loop that drives the pathfinding process. In each iteration of the algorithm, we meticulously select the node with the lowest f-cost from the open list. This chosen node is then moved to the closed list, signifying it has been evaluated, and subsequently, all of its neighboring nodes are carefully assessed. For each neighbor of the current node, we calculate its g-cost and h-cost. If we discover a more efficient path to that neighbor, or if it's a newly encountered node, We update its costs accordingly and add it to our open list for future evaluation. Once the algorithm successfully reaches the target node, the final step involves reconstructing the optimal path. This is achieved by backtracking from the target node, following the chain of parent node references all the way back to the starting node. Let's now implement the get distance method, which is crucial for calculating both the g cost and age cost. For grid-based movement, a simplified Manhattan distance is commonly used, calculating the sum of the absolute differences in x and y coordinates. When considering diagonal movement on a grid, it's common practice to assign a slightly higher cost to reflect the increased travel distance. For instance, a straight movement might cost 10 units, while a diagonal movement could be assigned a cost of 14 units. Back in Unity, create an empty game object in your scene and name it Pathfinding Manager. This game object will serve as the host for our pathfinding logic. Then, simply drag and attach our pathfinding script to this newly created game object. In the Inspector panel for the Pathfinding Manager, you will need to adjust the grid size parameters to match the dimensions of your scene. Additionally, assign the appropriate walkable mask to correctly identify and account for obstacles within your environment. To effectively visualize our grid and the calculated paths, we can integrate an onDraw gizmos method into our script. This powerful Unity feature allows us to draw debugging aids directly in the scene view, greatly assisting in understanding and debugging the algorithm's behavior.
After saving your script, return to the Unity editor. With the Pathfinding Manager game object selected in the hierarchy, you should now observe the grid visualization appearing directly within the scene view, providing immediate feedback on your setup.
Now, let's create a simple agent that will utilize our pathfinding system. For this, we can use a basic sphere game object. Add a new C# script to this agent, perhaps named Agent Movement, which will control its navigation. Within the Agent Movement script, we will obtain a reference to our pathfinding script. Using this reference, we will then call the findPath method, passing in the agent's current position and its desired target position to receive a list of nodes forming the optimal path. Once we have the list of path nodes, we will iterate through them, systematically moving our agent from one point to the next. This process simulates smooth movement along the calculated path, allowing the agent to navigate the scene effectively. Back in the Unity editor, assign the Pathfinding Manager game object to the corresponding reference slot in the Agent Movement Scripts Inspector. Additionally, create and assign a target game object that your agent will attempt to reach. Press play in Unity and observe your agent in action. It should now gracefully navigate through the scene, intelligently avoiding any obstacles, and ultimately reaching its designated destination by following the path calculated by the A** algorithm. For significant optimization, especially in larger or more complex environments, consider implementing a min heap or a priority queue for your open list. This data structure allows for extremely fast retrieval of the node with the lowest F cost, boosting performance. Furthermore, to enhance the robustness of your pathfinding system, implement a mechanism to handle dynamic obstacles or changes within the environment. This typically involves recalculating the path whenever an obstacle moves or a new one appears, ensuring continuous optimal navigation. Experimenting with different heuristic functions can yield varying results. While Manhattan distance is a common and effective choice for grid-based games, Euclidean distance might prove more suitable and accurate for environments with continuous movement spaces. It's important to remember that while A** is an incredibly powerful pathfinding tool, its performance characteristics are directly influenced by factors such as your grid size and the overall complexity of your game environment. Larger grids and more intricate layouts will naturally require more computational resources. Congratulations! You have now successfully implemented a foundational A** pathfinding system within Unity 3D using C#. This is a significant achievement and a valuable skill for any game developer. Keep practicing and exploring the myriad applications of A** pathfinding. By integrating it into various game mechanics and scenarios, you will continue to enhance your game development skills and create more dynamic and intelligent game worlds. Thank you for watching this comprehensive tutorial. We sincerely hope that the knowledge and practical steps shared here will significantly assist you on your journey to becoming a skilled and proficient game developer. Don't forget to like, share, and subscribe for more content.